Welcome to the 13th and subsequent lectures. In today's lecture and in the next few lectures, hopefully with over 3 lectures, we will cover the topics on uh, reflection and transmission characteristics. All right. So let's begin. We already know for a solid. Let me just pull out the pen. Yeah, we already know for an anisotropic solid the relation for stress and strain, and this is for a general anisotropic solid, and you have a simplified relation for an isotropic solid. Now, this is something which you guys are familiar with, and although I have written in tensorial notation, you know how to write it in vector as well as matrix notations. Likewise, there is a constitutive relation for fluids as well. The reason why I have to pull out fluids is often when we have boundaries, for example, if we have a plate, if this is the plate, it is surrounded by some fluid. Typically, it is air, the ambient air, right? Or water or some specific liquid uh, as suited to the purpose, right? So it is often required to incorporate this boundary condition between a fluid and a solid. That is the reason I thought I will introduce you all to a little bit on fluids, okay, at the beginning of this lecture, and then we will go ahead and work out all the uh, boundary conditions between solid solid and solid fluid and also fluid. Okay, I will not go into the details as to how this equation has been derived, but for now, we will assume that we have we will assume the authenticity of this equation. Okay, uh, so this stress tensor is minus pressure times identity tensor plus the second viscosity times gradient of velocity. Okay, u dot is velocity times the identity tensor plus another term involving the first order, another term involving the viscosity mu. Mu b is the second viscosity, mu is the first viscosity, right? So we will for now take this as granted. Okay, and those of you are interested can pick up any book by fluid, any advanced book on fluids. Okay, this is the corresponding relation, constitutive relation. Okay, we will restrict ourselves to inviscid fluids. Okay, and that makes both mu and mu b as 0, and hence our constitutive relation for a fluid. Okay, our fluids are all inviscid fluids, so the constitutive relation becomes sigma is minus p times I. As in, if you write the matrix form of it, you will get minus p 0 0 0 minus p 0 0 0 minus p, where p is the hydrostatic pressure. Okay, and continuity equation is same as before, right? So, and the momentum balance equation is this. This can be readily derived. You can look up the book by Kinsler. Okay, all you need to do is take an element and balance it out. It is equivalent to our del dot sigma plus v is rho dou square u by dou t square. Okay, and you substitute sigma as p times this, p times identity tensor, and that's what you will get. All right, pressure being compressive, you will get that minus sign. Okay, this equation is also called as Euler's equation. Okay, we have the continuity equation, we have the force balance equation, and we have the constitutive relation. Okay, all the three relations we have for a fluid. As we are dealing with inviscid fluids, the equations are simplified. Okay, let's proceed. And one other parameter which also comes in from thermodynamics is the phase speed of sound, which is given as square root of b by rho, where b is the bulk modulus. Now, for now, let us assume that we know this, okay? Because if we start deriving fluids, then we will end up with a wave mechanics course rather than an ultrasonic non-destructive evolution course. Okay, for now we will assume this is also something which is well established, and we will take it. Okay, so you combine all these equations. The equation which you would get is del square p is 1 by c square dou square p by dou t square. This is also called as a Helmholtz equation, or simply the wave equation for inviscid fluids. This is very similar to our wave equation in a string. Dou square y by dou x square, dou square u by dou x square is dou square u by dou t square times 1 by c square. It's very similar to that equation. Okay, just that this is in a three-dimensional form. And for plane waves, one can use the expansion of del square and write the equation as the following: a forward going wave and a backward propagating wave. All right. So this is the general form of plane waves in an inviscid fluid. All right. And as you know, the topic is today's lecture is on reflection and transmission characteristics. Reflection and transmission occur only when there is a boundary. Okay, reflection, transmission, scattering, diffraction, all of these occur when there is a boundary. The generic term is scattering. Okay, the special forms of scattering are diffraction, reflection, and transmittance. Okay. So we will consider reflection and transmission characteristics as well as refraction characteristics. So we will slowly introduce one boundary after the other. We will suddenly not solve problems like if this is the complex shape of an object, we will not study things straight away as if a plane wave is incident on it. How does the scattered wave behave? Okay, we will not directly get there. We will build up slowly. Okay. So let's proceed. So when you have two boundaries, when you have two mediums, there is an interface which is common to both of them. That interface is referred to as boundary. Okay, the interface of two mediums, we are going to refer it as boundary. And often you can have a wave going from one medium to the other medium. And we always have a reference as the normal of the interface as the reference. Any wave angle that we consider will be measured with respect to the normal. This is a convention which people have been following over the last few decades. We will stick to it. And we will denote mediums 1 and 2 as M1 and M2. And as you can see, the either of the mediums can be a solid or a fluid. Okay, so you basically have four combinations. Either this as fluid and this as fluid, top is fluid, this is solid, and this is solid and this is fluid, and both of them being solids. So you have about four combinations. We will study two, which will keep you in a good position to solve the remaining two. Okay, I will derive two. I will even get you started with the third one. All right. Now, as the fluids which we are considering are inviscid, they will only support longitudinal waves. And if at all the fluid has viscosity, only then it can support shear waves. All right, shear as well as longitudinal. All right. So we will take, if you can understand this, that's fine. But even otherwise, you can take this as a well-established concept. Fluids, we are not deliberately getting into the derivations of it. Okay. Now let's start with very simple thing. Solids, we had a long Navier's equation for a three-dimensional solid. So I thought I'll introduce you with fluids because first reason is often you have a fluid, you have one medium as fluid. Second thing is the equation, the governing equation is also relatively simpler, right? So let's start with analyzing if interface of a fluid and fluid. So I'm considering two fluids, I'm calling them as fluids 1 and 2. This is the notation which I am choosing, and wherever the wave is being incident, I'm going to call that interface as z is equals to 0. So this is not this is x is equals to 0. That's fine, right? I'm sending in one wave. So this dotted line is my normal. I'm sending in one wave which is at an angle in theta 1 with respect to the normal. And when I send in that wave energy, part of it gets reflected and part of it gets transmitted. Right? This transmitted wave is also called as a refracted wave. Basically, it is it is tearing through the boundary and getting in. That's why it's called refraction. All right. So a wave is incident, part of it is reflected and part of it is transmitted. Now, I'm not assuming this fluid layer to have some finite thickness. No, this fluid is infinite in this direction and the second fluid is infinite in this direction. That's what we are trying to analyze. We are not analyzing this multi-layered kind of thing. There's just two semi-infinite fluids. All right. So let us analyze this. As you can see, this is two-dimensional problem. So I chose a reference axis in terms of two basis vectors, x and z. So r is my corresponding position vector, xi plus zk hat. K is the wave vector of the incident wave. Let the wave number of the incident wave be ki, and you can write it in vectorial format, and you would get, so this is your z axis, this is your x axis, and I have a wave which is making an angle theta I, which means this vector k can be written in this form. I'm writing it in the vector component form, and correspondingly the pressure is p, which is this is the general form, pi times exponential I k dot r minus omega t. You know k, you know r. You substitute for both of it, and you end up for the incident wave as this expression, right? Likewise, we can see that the reflected wave is making an angle theta r with respect to the normal. Hence, the reflected wave number can be written in this style, and the transmitted wave or the refracted wave is wave vector is denoted by kt. And using simple vector notation, you can write kt in vector form, which means you can write the reflected wave and the transmitted wave in the corresponding simpler forms. So what is it that we are trying to analyze? When we say that we are having a fluid, we are having the interface of two fluids, and a wave is coming from the first fluid into the second fluid, which means we know the following. We know both the fluids, which means we know the material properties of it. And we also know the incident wave. I mean, we are sending a wave, which means we know what we are sending, right? The material properties of fluids are densities and the bulk corresponding bulk moduli. And the parameter of the wave will have an amplitude, a wave number, and a frequency, right? And we know at what angle we are sending the wave with respect to the normal. So these are the knowns. So what is it that we are trying to understand? We are trying to understand what are the reflection and transmission characteristics. So what are all the reflection and transmission characteristics? If you see the reflected wave, there is PR, KR, omega R, and the transmission wave, PT, which is the amplitude, and KT, which is the wave vector of the transmitted wave, and omega t, which is the frequency in the second medium, in the transmitted medium. So I basically have 6 unknowns. Okay. So let's see what are all the equations we know and what is it that we can get ahead with. So the first boundary condition, the boundary conditions in wave mechanics are same as those in elasticity, which is traction being continuous. Traction on one side is same as traction on the other side. All right. Okay. Then the second condition is, in elasticity, you often equate the displacements on both the boundaries, on the interfaces, right? Here, since wave mechanics is a dynamic process, the corresponding velocities are equated, because all fluid based equations are based on rate. In solid mechanics, we don't have the time derivative term when we are talking of stresses, but in fluids, it is always about rate. So these are basically the boundary conditions for all wave mechanics problems. Traction being continuous and velocity being continuous across the interface. Okay. So if traction is continuous, which means the pressures on both the sides should be identical. Ideally, this equation would be minus T1 is equals to minus P2. X is equals to 0 is my interface. So this will be my first condition, right? And what is P1? P1 is the pressure in the first medium. And what is the pressure in the first medium? In the first medium, there is an incident wave and there is a reflected wave, right? So I'm simply going to add them. So pressure in the first medium is equals to pressure in the second medium. In the second medium, the pressure directly is P transmitted because there is only one pressure wave there. So P incident plus P reflected is P transmitted. So we know the expression for P incident. We know the expressions for P reflected and P transmitted because we know the corresponding Ki, Kr, and Kt. Of course, Kr and Kt are to be determined, right? So we know the expressions for all these things. So I'm simply substituting equation 2 in equation 1. Okay, that's all I'm doing. So this is the expression I have, Pi times exponential this. But I know this expression is valid only at x is equals to 0. So I'm dropping the x is equals, I'm setting x is equals to 0 in equation 2, as in these three terms are being set to 0 because we are dealing at the boundary. This expression P incident plus P reflected is P transmitted has come from this by equating the traction on both sides of the interface. And the interface is at x is equals to 0. Right? So in equation 2, I am setting x is equals to 0 and substituting it in equation number 1. And doing that simplifies the algebra a bit. Okay, and this is the expression we have. And I am trying to take the time derivative term uh, separately in each of the three expressions. Okay, if you carefully observe this expression, this expression has pi, pr, pt, ki, kr, kt, and omega, omega r, omega t, where each of the omegas are the corresponding angular frequencies of the incident, reflected, and transmitted waves. Now, this equation has to be true for all values of z. Right? Z is this direction. This equation has to be valid for all points along the interface and at all times. Since z and t are independent variables, which means I can set the corresponding time variables to be the same. The only way that this expression holds true for all values of t and for all values of z, given that z and t are independent, is that the time terms are identical and the corresponding z terms are identical. Okay, these are two independent equations, two independent variables. So I'll first set the time derivatives. I'm sorry. I will first set the expressions of time to be identical. Then the remaining expression becomes an expression in terms of the variable z and no other variable. Right? See, z is varying along the interface. Right? No other variable is varying. The other variable, is time. So, and these are independent. So the only way this is possible is I set all the time terms to be 0, which will give me an expression saying omega r is same as omega t, and both of them are same as the frequency of the incident wave. So what this says is, when at a boundary, when you have a wave of a particular frequency, whether it is reflected or whether it is transmitted, the frequency does not get changed. This is why the frequency remains constant. Okay, it comes from the mathematics. And now that the time terms are set to be the same, the expression simplifies to this as equation 4. And the only variable here is z. And for this expression again to be valid at all values of z, the only way is these are constants pi, pr, and pt, and you have exponential terms. The only way this is possible is all the exponential terms should be the same. And hence you equate all the common phase. Remember, this was the phase, right? Whatever is there with iota, that is the phase. So I set all the phases to be equal. These are the three phases, and I've set this to be equal. And since these phases become equal, equation 4 simplifies to this pi plus pr is pt, because we are setting all the phases of the incident, reflected, and transmitted wave to be the same. All right. So setting the phase to be the same leads to this particular equation. And as z is common, I am removing z, which leads me to this particular equation. Right? And now I will use my phase velocity concept. Okay. And I will try to write k in terms of omega and c. Right? Omega incident is same as omega reflected, is same as omega transmitted. Right? Which means k, what is omega? Omega is k times c. Right? In medium 1, I am talking about the first medium, fluid 1 and fluid 2. Fluid 1, whether it is reflected or whether it is incident or whether it is reflected, the wave remains in the first fluid, right? Which means both these waves will have the same phase speed c or c1. So I know omega is same as omega r, which means k incident times phase velocity is same as k reflected times phase velocity. Since it is the same medium, we will have Ki is same as Kr. Since Ki is same as Kr, if I use this particular, the first two expressions and equate them, since they are already equated, right? And I set Ki is equals to Kr, I will get what is called as sin theta is sin r, which in otherwise is called as is commonly referred as angle of incidence is angle of reflection. This is something which you have been learning as a prescription, but now you know the proof of it. Likewise, I'll take the second two expressions, or even the first and the third expressions, right? So I'll take the first expression and the third expression. Ki sin theta is kt sin theta t. This is representing the incident wave. This is representing the transmitted wave. And I am writing the wave number in terms of the corresponding phase speeds. Ki is omega by Ci, kt is omega by Ct. Right? And now omega is same. So you will be led to this particular expression. Sin theta I by Ci is sin theta t by Ct, where C is the corresponding phase velocities in incident medium. If it is an incident medium, you call it, we are calling it as Ci, and if Ct is the phase velocity in the transmitted medium. Now this particular expression is the Snell's law. The reason for me to pick up fluid was also to make sure that all of us are clear on this basic concepts of angle, why angle of incidence is same as angle of reflection, right? And why does the speed, why does the frequency of a wave not change when it is moving from medium 1 to 2 to 3 to 4 and so on. So the frequency of a wave rarely changes in, or rather it does not change in linear elastic fluids as well as solids. Okay. So just by using one expression, the pressures, the total pressure being equal, boundary condition on the pressures being equal. How did we get this? We simply said the traction to be same on either side. Just using this one expression, we are able to get, say that the frequencies do not change, right? And that the angle of incidence is angle of reflection, and the last thing is Snell's law, right? Then let us continue with the same expression. After equating the phases, we have this expression, Pi plus Pr is Pt. We use this expression, and I'm going to divide either sides by the amplitude of the incident wave, and I will call Pr by Pi as in the amplitude ratio of amplitude of the reflected wave to the amplitude of the incident wave. I'm going to call this as reflection coefficient, a very standard term in wave mechanics. Similarly, I will define another expression called transmission coefficient, which is simply again similar to the reflection coefficient. This is the ratio of amplitudes of the transmitted wave to the reflected wave. Okay. So reflection coefficient and transmission coefficient talk in terms of the ratio of amplitudes of the pressures or displacements or velocities. Okay. Right now, in general, when people refer to reflection and transmission coefficients, they mean the reflection and transmission coefficient with respect to pressures or stresses. Okay. Not velocities, not displacements. They are not identical. Reflection coefficient with respect to pressures is not identical to reflection coefficient with respect to velocities. So in general, people refer to it as, when people say reflection coefficient, by default, they are meaning the reflection coefficient with respect to pressures or stresses. Okay, they both are the same. Okay, so with just by definition, we get this relation 1 plus r is t. And remember this, reflection coefficient and transmission coefficient are complex numbers. I should have written it. R and T are complex numbers. Reflection coefficient and transmission coefficient can be complex. And there are similar related terms which I thought I should introduce to you, which is the reflectance. This is the ratio of incident energy, ratio of reflected energy to the incident energy. And this is related to the reflection coefficient, which is modulus of R square. So reflectance is basically ratio of energies. Energies are never complex. So reflectance is a real number. Likewise, transmittance is ratio of energy transmitted to the energy incident. or ratio of transmitted energy to the incident energy. And you would get an additional term, additional factor with and not just modulus of transmission coefficient square for transmittance. And likewise, capital T is also a real number. Both are belong to the set of real numbers. Okay. Reflection coefficient and transmission coefficient are complex numbers, can be complex numbers. Whereas reflectance and transmittance denote the ratios of energies, and hence they are real numbers. In fact, mathematically, you will see it when you solve your assignments, you will actually see it. Now let's go to the second boundary condition. We are talking of two inviscid fluids, which means there is no corresponding speed at the boundary of the tangential to the boundary. So the boundary condition then simplifies to as normal components of the particle velocities must be continuous, right? So how do I identify the velocities? We will use the Euler's equation, which is rho d is dou square u by dou t square, which is the acceleration term, is equal to negative of gradient in pressure. How does this come? You can derive it. For now, let us accept that this is true and let's use it. We already know the generic expressions for pressures. All the while we have started with pressures. So let us use this expression and substitute this to identify the displacement. My pressure incident P in the first medium is P incident plus P reflected, right? Which means when I have to take gradient of P, I need to take gradient of P incident plus gradient of P reflected. What is gradient of P? Dou P by dou X, right? Dou P by dou X I hat plus dou P by dou Z. Here we are using the X and Z coordinate systems. This is nothing but grad P, right? And dou by dou X, you know, looking at the expression here, P was, we had the P incident as Pi times exponential I K X cosine theta I plus Z sine theta I minus I omega t. And you can take the partial derivative with respect to X and you will be left with Ik cosine theta I hat. Likewise, dou P by dou Z will give you Ik sine theta I P incident times the unit vector along Z. Similarly, you can take the gradient of the reflected wave and the transmitted wave. Now, let us use the condition that let's first identify the velocities, then we can set the boundary conditions. So the incident velocity is P would be this incident velocity of the, wave, particle velocity of the incident wave. Excuse me. Likewise, the corresponding particle velocity of the reflected wave can be written in terms of the gradient of the reflected wave. How did this come? I hope you guys are now familiar with taking partial derivatives. For the benefit of all, let me just expand this. So we have already identified the gradients. What is rho dou square u by dou t square? Dou square u by dou t square, we know the time dependence is minus I omega t. So which means the partial derivative with respect to time is minus omega. We have a second derivative with time. So this is what our rho dou square u by dou t square term simplifies as. And this expression rho omega square u minus into minus is plus, I into I is minus 1. So that is why I am dividing this expression with whatever I have as gradient P. So I have rho dou square u by dou t square is minus grad P. Rho dou square u by dou t square is minus rho omega square vector u is minus grad P, which means I need to, my expression for u is grad P by rho omega square. And that's what I'm doing. That's why I'm dividing it by the rho incident omega square for the first expression. Reflected is also in the same medium, rho incident. So not rho incident, rho I. whereas the transmitted wave, the density is rho t, right? And that's why I have this multiplication, this denominator. So using the second boundary condition, velocity is normal to the interface. The interface is along the z direction. Normal to it is x. So simply the I need to equate the velocities in the x direction in both the mediums. In the first medium, adding these two terms, ui plus ur, vector u plus vector r in the I hat direction, in the x direction, is this expression, which is the normal direction, right? The normal is x direction. So velocity is normal to the interface should be identical. So this is the velocity, net velocity, one due to the incident wave and one due to the reflected wave. And this is the velocity perpendicular to the interface in the transmitted medium, right? And rest of it is algebra. So I'm taking the common term, right? Omega is same. So that has been removed. And I am writing the same expression in terms of reflection and transmission coefficients, right? What is R? PR by PI. T is PT by PI, right? So I will end up with this expression. 1 minus R is this, 1 plus R is this, right? And I'm going to solve, I have two unknowns, R and T, and I have two equations. What are these two equations? The original equation was 1 plus R as T, which is what we got from the first boundary condition. I have 1 plus R as T, and I have now one more expression, 1 minus R times a particular term and 1 in terms of T. So use these two equations, use the relation K is omega is equals to Ck, so which means K is nothing but omega by C, right? So Ki is nothing but omega by Ci, right? And Kt is nothing but omega by Ct. So all I am going to do is two equations and two unknowns. What are the unknowns? R and T. And I'm trying to write everything in terms of the phase speeds, because phase speed is a material property, whereas wave number K has both experimental parameter, which is frequency, and also the material property C. So two equations, two unknowns, you solve for it, and you will get these expressions for reflection coefficient and transmission coefficient. As you will see, I have used the incident medium as I, transmitted medium as T, and that's how I have been referring to in this lecture. You can, some books call the incident medium as 1 and the reflected medium as 2, and which means your density rho I is nothing but rho 1, right? And the space speed C1 Ci is equals to C1. It's just an algebraic notation. Okay, but the key point is this: your reflection coefficient for a plane wave is dependent on the material properties rho t, ct, rho I, and ci, as well as angle of incidence and angle of transmission. We know angle of incidence. Since we know the fluids, we know rho I, rho ci, rho t, and ct. But how do we identify theta t, which is the transmitted angle? We will use the Snell's law. Okay. The material properties are known. The angle of incidence is also known because we are performing the experiment. The only unknown in expressions of T and R is theta T. The way you identify theta T, which is the transmitted angle, is by using Snell's law. All right. So we will stop at this place, and in the next lecture, we will continue from here. All right. So in this lecture, we have seen how the reflection and transmission characteristics can be analyzed in terms of reflection and transmission coefficients for a plane wave incident and from incident at the interface of two semi-infinite inviscid fluids. All right. So we will continue the same topic in the next lecture.